Good afternoon. Thanks so much for being here. It's not a full house, but better than nothing. Yeah, it's good for tomorrow, yeah, and the weekend. Everybody's working. So again, this is my TRB presentation, or poster actually, which I converted to a presentation for the Ken seminar. The title is Potential Moisture Damage of Asphalt Mixtures Using Various Test Mechanisms. Let me start by thanking my co-authors, Dr. Qazi Aurangzeb and Professor Imad Al-Qadi and Professor Hassan Uzair, for their contribution to this work. The outline of this study will start first with a brief background about moisture damage. Then we will discuss the problem statement. Why did we do this study in the first place? Then moving to the objective and the scope of the study. And then in details, I'll discuss the two mixture level tests I used in this study, which is the Lotman and the push-pull tests. Moving forward to the materials and the experimental plan developed and implemented. Toward the end, I will show you the results and the discussion, and finally, toward the end, wrapping up with the conclusions. Moisture damage, briefly, is defined as a degradation of asphalt concrete mechanical properties due to the existence of moisture. And the susceptibility or sensitivity of asphalt mixture to moisture basically depends on several factors. Most importantly, the aggregate and binder that we are using in the asphalt mix, the mixture characteristics between those two components, the climatic conditions, of course, this is so important, the pavement design, and the traffic loading. It is good to know that 70% of our roads here are suffering from this phenomena, the moisture damage. When moisture exists in asphalt concrete, it deteriorates the asphalt through two main mechanisms: the loss of adhesion, where the bond between the aggregate and the asphalt binder weakens, and loss of cohesion, where the bond within the binder itself starts to weaken. Now, the problem statement, why did we do this study? For your knowledge, transportation agencies, when they face moisture damage or when they know that they have a moisture susceptible mix, they tend to follow one or more of the following approaches. Either or they use an additive or modifier added to the asphalt mixture in order to enhance the bonding between the asphalt binder and the aggregate, so making it more moisture resistant. They make sure that they build an efficient drainage system. It's inevitable that we will, at the end, have moisture in the pavement. But the key here is that we need to get rid of that moisture as fast as possible. And also, it's good to have a strict QA/QC for the asphalt pavement, starting from the production and the asphalt plant toward the end, which is the construction. Another challenge for moisture damage is that how are we going to evaluate the moisture susceptibility of asphalt mixtures in the lab? There are a lot of laboratory tests in which we can indicate that this mixture is moisture susceptible or not. But most of the time, those mixture level tests or those tests share some drawbacks, which is first, empirical tests. They are not, unfortunately, built on fundamental properties of the asphalt mixture. So you can guess that the results will keep changing. There are limitations on the simulation of the pavement climatic condition that the pavement suffer in the field. And that's also a major drawback. One of the major drawbacks also is the lack of correlation between the field and the lab results. So maybe in the field you will find the mix is moisture susceptible, but when you test it in the lab, it's not, and vice versa. So because of that, and the time of this study, we were starting to play with the push-pull test. It's a new test at that time in our lab. So we wanted to see if we can capture or we can evaluate the moisture susceptibility of asphalt mixes using that test. So with this being said, that takes us to the objective of this study, which is briefly to evaluate the effectiveness of liquid anti-strip agent and hydrated lime on reducing the asphalt mixture moisture susceptibility using the push-pull test. We have two major mixture test used in this study, the push-pull test and the Lotman test, and we will talk about them in details in the coming slide. Conditioning-wise, we have conditioned the samples under the dry conditioning state and the also a set with 5 freezing thawing cycles. So the scope of the work will be first selection a moisture susceptible mix, the additives, which is lime and liquid and strip as mentioned in the objective. We were going to develop an experimental plan on which we'll at the end going to implement, and the results will be gathered and analyzed toward the end. So what is the Lotman test? Lotman test is the typical test in the US used to evaluate the moisture susceptibility. Most of transportation engineers know that this test is used in the different agencies to evaluate for the moisture susceptibility of asphalt mixtures. And usually the dimensions for the sample used for this test are is 95 millimeter in height, 150 millimeter in diameter. We usually, for each asphalt mixture, we prepare 2 sets. One set we call it unconditioned set, which we don't condition except we just put them in for 2 hours in a 25 degrees water bath and then test it. And the other set, which is the conditioned set. Now it's depending on which state you are working. In Illinois, we have our Illinois conditioning procedure. You can also have 1 freezing thawing cycle, 2, 3, as much as you desire. 2 parameters we take out of this test: the indirect tensile strength, the IDT, and we call it indirect because we apply compressive load, but really what we are focusing is the tension test that we are getting from this test. The second parameter is the tensile stress ratio, which is basically the IDT for the conditioned set with relative to the IDT of the unconditioned set. The second test, which is the push-pull test, which is a relatively new test in our lab. This test uses the viscoelastic continuum damage theory in order to assess the fatigue properties of the asphalt mixture. It applies cyclic loading, tension, compression until failure. And it was recently used before my study to evaluate the fatigue properties and the fatigue performance or behavior for the mixes with wrap. Actually, Dr. Kazi, who was a student here, used this for mixes with 50%, 40%, and 30% wrap. In this study, we conducted this test under strain control mode. Actually, we cannot conduct it here except under this mode because we don't. It's not ready for the stress. We don't have the equipment ready for the stress control mode. It was at frequency of 10 hertz. The test was conducted at 10 hertz. We have used 3 strain levels, 200, 250, and 150 microstrains, and at 2 temperatures, 20 and 10 Celsius. The test was performed until 150,000 cycles or until the samples failed, whichever comes earlier. Also, it was tested on 2 sets, unconditioned and conditioned. Here, unconditioned, we don't put it in water whatsoever, prepare the sample, test it immediately. The conditioned set, again, could be in a procedure, Illinois modified, 2, 3, but again, as mentioned in the objective, it was only 5 freezing thawing cycles in this study. Dimension samples, similar to the samples used to measure the complex modulus of asphalt concrete. 150 millimeter in height, 100 millimeter in diameter, and we will see why it is similar to the complex modulus samples. The parameters, the pseudo stiffness, which is C, versus the damage parameter S. Pseudo stiffness is basically the amount of drop of the complex modulus at each loading cycle compared to the initial complex modulus that we started the test with. And that's why we use the complex modulus. We need the initial value of the complex modulus. That's why we need to run the complex modulus before we test the sample for the push-pull test. And also the second thing which is important, the number of cycles to failure. This is a fatigue test. So we need to know the number of cycles to failure as we get this parameter from any fatigue test. This is the setup of the push-pull test. As you can see, this is the complex modulus sample, similar dimension. We glue it to a bottom and a top cap, and then we screw those caps to the fixture. And then, as you can imagine, we apply tension, compression, load until failure, and those are the extensometers that measure the deformations. Materials used in this study, we made sure that we use a moisture susceptible mix, and in this case it was N90 19 millimeter nominal maximum aggregate size binder mix. It was moisture susceptible based on IDOT specification, meaning that the TSR, or the tensile stress ratio of this mix, was less than 85%. In Illinois, if it is less than 85%, it is a moisture susceptible mix. And the samples were conditioned with only one thawing cycle. Additives used, again, I forgot to mention that this mix is from District 5. The additives was liquid and strip, brand of paved grip Pipe 50, and this is also used in District 5. So in District 5, when they need to add liquid and strip, they use this liquid and strip. And we used 0.75% by the weight of the binder. So liquid and strip was added to the asphalt binder. For the lime, we added 1% lime, and we added to the aggregate. So 1% by the dry weight of the aggregate. This is the experimental plan. I will not go in details, but as mentioned, there are 2 tests. For each test, we have now 3 mixes: the control mix, which is a moisture susceptible, the same mix with liquid and strip, and the same mix with lime. All have the same aggregate gradation, everything. The only difference is the liquid and strip and the addition of lime and liquid and strip. And for each mix, for each test, we tested 2 sets: the unconditioned and the conditioned. And again, the conditioned was every time 5 phasing thawing cycles. 5 phasing thawing cycles, what does that mean in more details quickly? So when we prepare the samples, we measure the volumetrics of each sample, meaning we measure the air voids, the amount of air voids in each sample. We saturate the sample by using a vacuum. Saturating mean here filling 70 to 80% of the air voids of that sample with water. Then of course we wrap the sample with saran wrap, then in a plastic bag. We add 10 milliliters of water. After that, we place it in a freezer at -18°C for at least 16 hours. After this is done, we place the samples in a 60 degrees water bath for 24 hours. Now, with that, we finish 1 phasing thawing cycle. So since we are doing 5 phasing thawing cycles in this study, so we repeat this step again another 4 times. With that, we have 5 phasing thawing cycles. The last thawing cycle, we take the sample from a 60 degrees water bath, put it for 2 hours in a 25 degrees water bath, and then the samples are ready for testing. This is an IDT sample. The same thing was done for the push-pull sample, but of course the sample dimensions are different. Lime addition, there are several addition techniques for lime. In Illinois here we have 3 techniques: slurry, we have wet, we have lime. The method that we used in this study was the dry technique, which is basically we batch normally the aggregate, but without the mineral filler, of course, and dry it in the oven for 2 hours at least to make sure that all the moisture is evaporated and the temperature is 295 Fahrenheit. Then we take it out, add the 1% lime, and also after that we add the mineral filler, put it back in the oven just to make sure that the batch goes back to the mixing temperature, and then we finish. We go ahead and continue with the normal mixing and compaction procedure. Now moving toward the end, to almost the last part of this presentation, which is the results that we got from the conducted test. Starting with the Lotman test. Now the Lotman test, as described earlier, and we are using IDOT specifications for this study. Although we are using 5 phasing thawing cycles, and in Illinois, the Department of Transportation, they use 1 thawing cycles, but we are going to stick with these specifications. The tensile strength threshold for unmodified mixes, which is our mixes, because we use PG64-22 unmodified binder. So the tensile strength threshold is 60 psi. Lower than 60 psi means that the mix is weak. The TSR threshold, the tensile stress ratio, is 85%. So if your mix is less than 85%, having a TSR less than 85%, this means that it is a moisture susceptible mix. Going to the results, this table we have the results for the 3 mixes. The first column is the unconditioned tensile strength. There is no conditioning. The second column is the conditioned tensile strength, which is after 5 freezing thawing cycles. The TSR is the last column. So if you look at the first column, we can see that the control mix barely exceeded the threshold for the which is 60 psi. Addition of lime contradicts really here with what is mentioned in the literature. It is well known that lime usually increases the stiffness or the strength of the mix. Here, 1% was not enough to do any significant alteration. So it's 59.6, very close to the threshold. While liquid and strip, the addition of liquid and strip have dropped the tensile strength compared to the control, which agrees with the literature because liquid and strip is believed to soften the mix, so reducing the sort of the strength or the stiffness of the asphalt mix. But if we go to the conditioned tensile strength, we can see that, which makes sense, all of them are dropped in relative with the unconditioned tensile strength, which makes sense again. But the important numbers are at the end. The huge drop was realized or was seen for the control mix. Only 45% of the tensile strength was sustained after 5 freezing thawing cycle. So a huge drop in the control mix after conditioning. While for the lime and liquid and strip, the performance was better. Only 77 and 85.7 was sustained after conditioning. The best, of course, the performance was here for liquid and strip. In other words, strength-wise, this is the weakest one, but moisture resistance-wise, it is the best. So it was able to sustain the most of its load after 5 freezing thawing cycle, and 5 freezing thawing cycle is a lot for asphalt mixes, especially this weak mix. This is the first test. The second test, which is the complex modulus. As we said, complex modulus is a prerequisite for the push-pull. You cannot test the push-pull. You cannot test the samples for the push-pull except after you test them for the complex modulus. You need to know that value to input it as an initial value. So this is the fixture for the dynamic modulus. I'm sure that most of you are aware of it. And these are the master curves and we have 6 master curves, 3 for the unconditioned and 3 for the conditioned. And because we have three mixes. Looking at only the dry or the condition or the unconditioned states, we can find that the lime and the control are very close to each other. But since liquid and strip, as mentioned, softens the mix, so it came below them. So the complex modulus of the mix with liquid and strip is lower. But if we compare each mix unconditioned state with its conditioned state, we can see there's a drop of the master curve. Now, it came to our knowledge that some researchers have used this test or check this test if it's able to capture the moisture susceptibility or sensitivity to moisture for the asphalt mixes. And what did they do? They measured the complex modulus at 21C, and at each frequency at 21C, they found what we call the E-star ratio, in which they divided the E-star or the complex modulus of the conditioned with relative to the unconditioned, which is similar to the idea of the TSR. Numerically speaking, this is what I did. So for the control, the E-star ratio was 61 to 55. We take the average of this. That's what they did. It is 57.6. Similar for the lime, it's 58.4. And finally, for the liquid and strip, it's 72.4. What this is saying is that there is a almost 50% drop in the complex modulus for the control and the lime after 5 freezing thawing cycles. While for liquid and strip, 72% was still sustained of the original complex modulus after conditioning. So ranking-wise for liquid and strip, it performed, again, moisture sensitivity-wise, it performed the best here and also in the Lotman test. But the ranking is different for these two, and this could be because of the mechanism. Here we apply only pure compressive strength. For the Lotman, we apply compressive, but we look at the tensile. So this could be the difference. But again, we're not looking at this. We want to compare the push-pull and the Lotman. But it was like worth, because since we tested, it was worth of looking at the values from this test. The last test, which is the push-pull test. This is the results that we get from the push-pull test. This is the preliminary results, which is the pseudo-stiffness versus the number of cycles. And this is a sample result. This is for the liquid anti-strip conditioned mix after 5 freezing foaming cycles. We have 4 samples. We test 2 of them at 200 microstrain, 20 Celsius, and the other 2 at 250 microstrains at 20 Celsius. From this curve, we get what we are really focusing what we really want to look at is the pseudo stiffness versus the damage parameter. Again, we have 6 curves because we have 3 mixes and 2 conditioning sets, unconditioned and conditioned. And as you can guess, the higher the curve, the better the performance, because as we increase the damage, the amount of decrease in the stiffness is less. So, which means that the material still resists more the damage. So if you look at only the unconditioned state mixes, the control, then lime, then liquid anti-strip comes in this ranking. The best is the control, then lime, then the liquid anti-strip, which is sort of, you still remember, the same ranking that we got from the Lotman test, looking only at the unconditioned tensile strength. If you look at the condition, so after 5 freezing foaming cycle, the ranking is liquid anti-strip, lime, control. So the question is, how are we going to report this? Which damage parameter should we stop at and say, okay, at this damage parameter, we have this mix is better than this mix. So I mean, since we only have 3 mixes, we cannot like build a solid conclusion. So we thought that, okay, why don't we take all the curves? We compare the curve of each mix between its unconditioned and conditioned, and find the sum of square error between those 2 curves for each mix, and see what values are we getting. And that takes us to the third figure here. As you can see, the sum of square error for the liquid anti-strip is almost 0, meaning that the difference between the C versus S curve of the liquid anti-strip condition and the unconditioned is almost minimal. There was no effect of the 5 freezing foaming cycle on the liquid for the liquid anti-strip mix. Slightly higher for the lime, 6, but a huge drop for the contour. And as we can see, the contour is the black curve, the curve which is the highest, and this is the unconditioned. The condition is the blue curve, so a big, huge drop after we condition the control mix. And if you still remember, again, the TSR values, this is the same ranking that we got from that test. This is the last figure, which I want to talk in more details. I mean, maybe it's not directly related, but it gives us more ideas about the push-pull test results. I want you to focus on the liquid anti-strip and the lime for the moment being, and let's forget about the contour, which we'll come to talk about it later. Now we know that this is a fatigue test now. And we know for fatigue test, when you have a softer mix, then it requires a higher number of cycles to failure. This is basically a fatigue, let's say a rule, for example. And as we saw from the complex modulus results, when we condition the sample, the mixes, they all get softer and they had the lower complex modulus compared to their original unconditioned mixes. So, which means here, if we are going to run this test at a strain control mode, what we see, which is a little bit misleading, is that the number of cycles to failure for liquid anti-strip mixes after conditioning is higher than the number of samples, than the number of cycles to failure for the liquid anti-strip unconditioned. Again, number of cycles to failure for the liquid anti-strip conditioned mix, conditioned mean went under 5 freezing foaming cycles, compared to is higher, much higher, to the number of cycles required to failure for the liquid anti-strip mix before conditioning. As if what I'm saying is that condition your mix and it will perform better, which is misleading. We know that when we have in the field, when there's a lot of freezing foaming cycles happening in the pavement gets weaker and deteriorates very quick or faster under traffic loading. This is not giving us this result. Similar to the lime, you can see that lime, number of cycles for lime conditioned mixes is higher. Number of cycles of failure for lime conditioned mixes is higher than the lime unconditioned mixes. This is a misleading finding too. So what's the issue here? So again, It seems that this test, in order to be representative of what's going on in the field, we need to run it on a stress control mode, not a strain control mode. Because what's really going in the field is that we are applying stress after stress after stress on the pavement. We're not applying strain. And I know this is a big debate in fatigue test. But for this test, in order to give us a good, at least, prediction for the performance in the field, we need to consider that. Now, for the control mix, we had the two cases. At the lower portion, at lower macro strains, the number of cycles of failure for the condition is higher than the unconditioned. But when we started going for the higher macro strain, things become more logical, where the number of cycles for the unconditioned is higher than the conditioned. And this is another conclusion. Maybe if we need to compare for the same mix between its unconditioned and conditioned states, we need to use two different macrostrains. So maybe we need to use a lower strain for the conditioned and a higher strain for the unconditioned in order to at the end compare apples to apples. Now, so what did we find so far is that push-pull test is giving us the same ranking as the Lotman test. And if you ask anybody who ran both tests, and you ask him to run it for moisture sensitivity, he will tell you immediately, I will go with the Lotman test because it's relatively easier, less time consuming, and less effort too. But so the question, so why push-pull test at the end? Why should we use it at the end? So as authors, we discuss this a lot. The thing is not only we look at the test in the lab that's easier or not easier. There are a lot of benefits that we can get sometimes from tests which uses a lot of time. Some properties that can give us better prediction about the performance and the behavior of the that happens in the field. One of them is that we know that the IBT or the Lotman test is a strength test that tests the mixture in a very extreme conditions. Meaning, you will never see in the field a pavement loaded until it fails. You will always see cyclic loading coming on the pavement, track after track, stress after stress. And this is more simulated in the push-pull test than in the Lotman test, because we apply cyclic loading, tension, compression until failure. One more thing, Lotman test gives you a snapshot of the material. You only get one value from the Lotman test. That's it. It's tensile strength. You will get the TSR, of course, but it's also a reflection of the tensile strength. So you only get one thing out of that test. But from the push-pull test, when you run many samples at different temperatures, at different macro strains, you can have a huge map about the performance and the behavior of the fatigue behavior of that mix at any macro. You can predict the performance at any behavior, at any macro strain, at any temperature, and that's something you will never get from the Lotman test. One thing that I kept saying more than one time in this presentation is that you get the tension failure from the Lotman test, but by applying a compressive load. So why don't we go to a test that applies a direct tension test, which is more influential to the asphalt mixture that we are testing for the moisture sensitivity. Okay, so the conclusion at the end, complex modulus, as mentioned, evaluates the asphalt mixtures under compressive loading, while the push-pull do that under cyclic tension and compression forces. The push-pull test appears to simulate the long-term field loading conditions, and it can be used, as shown, at least for our three mixes to assess the moisture susceptibility. The tensile-based test, because we have tension failure and we have tension failure in both tests, the Lotman and the push-pull, they result in the same ranking for the three mixes. We saw that liquid and strip and lime in both tests have resulted in reducing the moisture susceptibility of the asphalt mixes. And based on the results of this study, we found that it's better to run the push-pull test if we want to see better prediction of fatigue in the field under stress controlled rather than strain controlled. And finally, it seems to be a promising tool, the push-pull, but of course we need to run this test for more than 3 mixes. We need to run it for different types of mixes. We have SMAs, we have warm mix asphalts, we have fine mixes, we have mixes with RAP, we have mixes now with RAS. We need to run this test at all these types in order to come up with a very good and solid conclusion. With that, I would like to acknowledge the Illinois Center for Transportation, of course, IDOT, James Trepanier, and the other TRP members for their valuable input, and of course, our wonderful research engineers, Jim Meiser and Aaron Conner. Thank you so much.
No questions.
We just want to leave. So either you didn't understand anything, guys, or I was so good.
On everything. How do you talk to the plates onto the specimen when it has been conditioned in water? How do you make sure?
No, we do that after conditioning with water.
Yeah. So how do you make sure the specimen is dry enough so you get good bonding?
What I did is just put them in front of the fan for 20 minutes, and you can see that the surface became dry. And by the way, when I put that glue, I leave it for 8 hours. So usually, and so I leave it. I mean, you should keep it for 8 hours according to the specs of that material, but usually I keep it for the next day. Yes.
Is there a way to determine the degree of saturation in the specimen?
Yes, of course. If you know the exact air voids in the specimen, yes, of course you can, and you know the volume of the air. If you know the volume of the specimen and you know the volume of the air voids, then you can know exactly how much amount as weight of water to fill in that specimen. Yes, you can.
You actually came in just after that slide. You explained the saturation process.
Oh.
Yeah, you can, of course.
Saturation.
Oh, okay.
So when I saturate my samples, I saturate them, and I know. So when I put the sample in the water, close it, saturate it, and then I wait for 3 minutes or 4 minutes of saturation in that vacuum, and I weigh the sample. I know, according to my calculation, is that this sample is 70, 60, 50, 100% fully saturated with moisture. Yes, we know.
Was there any consideration to the different types of machines it takes to run a servo hydraulic machine versus a screw press machine for the allotment versus the push-pull? As far as, is there any consideration yet to actually putting it in the field as far as QC labs? It's just a still experiment.
Yeah, that's a good question. I mean, for practical side, you mean?
Yes.
Yeah, I mean, I know that even if at the end, if for example, run the push-pull test for all these mixes, and it's proven to be a very, very good tool. Yeah, that's another part. I mean, that we need to consider to how to convince the contractors to have this big machine on. Especially, it's time-consuming. I admit, but again, I mean, you are having more than one bird in one stone. You will have moisture susceptibility of the mix. You will have the fatigue, a good idea about the fatigue performance of the mix. So as if you are running a fatigue test and a moisture susceptible test. At that. Yeah, 2 in 1. At least that's what I know.
That's all right.
Okay, thank you.